Hello everyone, I'm Sumni Shin, Assistant Professor in National University of Singapore. First of all, it's my honor to win the Women in Science and Technology Award and deliver my talk here at AKC 2021. The topic I would like to present today is my research on the thermal engineering using photonic structures. So basically, I employed optical engineering to control heat, and in particular, I'll be presenting on my experimental platform to prove the coherent thermal emission in a single nano-object. In general, there are lots of applications requiring the thermal engineering, and it's simply from the heat dissipation and renewable energy, thermal insulation, or regulation for the buildings, and to the next generation memory devices as well. However, there is a critical challenge in the heat transport. It has a lack of controllability, and it's because the dominant heat transport process is diffusion. So it goes to everywhere. As examples, your thermometer, it stays hot temperature only up to 5 hours. Once there is a temperature gradient hot to cold side, with the picture of diffusion, the interface cannot effectively block the energy. It's hard to avoid the heat flux from hot to cold side. This feature is clearly different from light, which has phase or polarization. You can block the incoming energy, which is electromagnetic waves, by changing the direction of its propagation, which is reflections. So you know that you can achieve it even up to 99% of reflection. It has been very clear that optical engineering has shown well advanced controllability of light energy. For examples, you can localize the light in a very confined space, or you guide a wave in the long range. My strategy to advance the thermal engineering to have better control is that we mimic the optical engineering. Especially, I focus on the radiative heat transport, where photons are contributing to the heat transport. At final temperature, any object can radiate electromagnetic waves. Then, can it be the same as light? Here's a different point. Radiation consists of electromagnetic waves, but the hot object radiates energy in all directions, which is like incandescent light bulb, and also followed by the Planck's law. It has broadband energy distribution at each temperature. So it doesn't have a sharp control in direction of the heat transport and also in frequency, which is energy. Before I go into the details of my research design, I would like to start with some brief brainstorming to compare the radiation and heat conduction process. Firstly, the radiation. Hot object emits electromagnetic waves, and it doesn't require medium, so it's more dispersive. Its wave feature has been considered as a ballistic transport, and the energy carriers of electromagnetic waves are photons. In vacuum or air, the group velocity is light velocity. And now heat conduction. It requires a medium. This is the diffusion process, and it can be described by the particle motion. The energy carriers are phonons. Their group velocity is sound velocity, and it will be much lower than the light velocity. For example, in air, the light velocity is about 3 and 10 to the power of 8 meters per second, but the sound velocity is below the 400 meters per second. It would be good to take the advantage from both. For example, I like the fact that radiation is fast and its transport is not limited to the physical size of the object. But I also like the fact that the conduction has more confined energy guided through the solid. So then, is there any way to combine those different advantages from radiation and conduction? Here I compare the two different energy momentum dispersion curves for photon and phonon. Radiation by photon will follow this sharp straight line, which is omega equals to ck, and here the c is the light velocity. For phonon conduction, the dispersion is determined by the atomic structures, and you can clearly see it's more flat than the light line. So that when these two different energy dispersions can interact each other. At the surface, when photon and phonon energy carriers can meet, they can form the coupled energy state of photon and phonon. But it needs to be the same energy. For example, the polar dielectric, silicon dioxide, silicon carbide, or hexagonal boron nitride, those has their intrinsic resonance frequencies in the polar atomic bonding. In particular, the resonance frequencies determined by the optical phonons has the same energy like infrared wavelength of photons, which is around 10 micrometer. This 10 micrometer wavelength energy also corresponds to the room temperature. That is an interesting point. At around the room temperature, the radiating energy at the surface can be coupled to the optical phonons in the solid. It makes the radiation confined at the surface. And the surface has the unique dispersions. And as you can see, the specific energy band it shows these unique features. And these energy regions we so called the Radiative band. And these bands are defined by the two resonant frequencies determined by the optical phonons. And these features are pretty similar to the surface plasmas if you are familiar with this concept. But of course the energy range are the difference. The surface phonopolarity happens in the infrared. And you will see later from my research how the radiation was controlled in these energy rhythms. And my next question is how to emphasize the surface effect. We can improve the surface volume ratio by making the nanostructures. Indeed, Max Planck also mentioned in his textbook, saying that the Planck's law assumes the large object compared with the wavelength. The radiation of the nanostructures will not follow the classical Planck's law. In optics, people have realized a strong and selective spectral response with the silicon carbide nanoparticles and directional emissivity with silicon carbide grating structures. This distinct spectral and directional emission will give us different pictures from the black body radiation following the classical Planck's law. But measuring the thermal emission from nanostructures need to handle the nanowatt scales of the thermal power. So most of the experimental was being done by the optical measurement, but not the thermal measurement. Here are my designs to observe the non-Planckian emission from the nanoscale emitter. The coherent feature I target is sharp control in spatial and spectral distributions of the thermal emission. I choose the silicon dioxide, which is a glass, one of typical polar dielectric materials. Now we will look at the spectral emission. The bulk glass is almost black body, so it has a broadband emission spectrum and very close to the Planckian black body limit. To observe the enhanced signal, we want to remove the classical broadband emission features. So we reduce the thickness below the skin depth. To meet the energy conservation, absorption equals to emittance. By making a thin structure, we can reduce the absorption capability. So as you can see from this plot, now we suppress the broadband emission. And now we control the width, and we will study the size effect. How we can enhance the emission. We expect to have the enhanced emission, especially at around the 10 micrometer wavelengths by surface phonon polydens. Energy at those two peaks are related to the optical phonons resonance frequencies, and this is the main strategy to observe enhanced emission with the controlled size of this random ribbon-like structure. We developed a new measurement platform to detect the far-field thermal radiation by using the suspended thermometry. As you can see from this schematic and SEM image, the nanostructured emitter that will be located across the suspended heater and sensor so that we can estimate the thermal power by monitoring the temperature. Later, we extract the emissivity value. This is a device with a suspended object. Apply current to heat up the one side of the metal beam by the joule heatings, and the heater beams are connected to the thermal reservoirs, so the temperature profile will have the maximum peak value at the sample edge. And we measure the increased temperature by measuring the voltage. The metals have intrinsic parameters called TCR, which is the temperature coefficient of resistance. The resistance of the metal beam will be changed in response to the temperature. So the measured voltage change will detect the temperature change. And now, since we heated up the one side of the samples, there will be the heat flux across the samples, and similarly we'll measure the voltage to detect the temperature. With and without the radiation, obviously we'll measure the different temperatures. When there's no the heat loss by the radiation, from the heater to sensor, you will have a linear temperature drop, which is determined by the photonic conduction across the samples. On the other hand, if you have a radiative heat loss, the temperature drop will be faster. So by quantifying the difference, you would know the radiative heat transfer coefficient. We use a Fit model to quantify the temperature profile. And first of all, the temperature drop is exponential, and the decaying rate is weighted by a Fit parameter M. This M consists of the radiative heat transfer coefficient and thermal conductivity, and all dimension information as well. So once we know M parameter, we can quantify H. H is a heat transfer coefficient, and eventually emissivity. To extract the emissivity in my experiment, I control the length of samples. And for short length samples, you will not see the difference much with and without the radiation. But for the longer length, you will see the significant temperature difference. Here I compare the emissivity for different sizes of samples. And I need to emphasize that this is the first experiment demonstration to measure and quantify the emissivity from the suspended single nano object for far-field radiation study. Okay, now let's look into the result. The thin-film result is modeled emissivity, and we can consider this as a baseline to see the enhancement in our experiment. And I have two experimental results with around 10 and 5 micrometer width. So, you can clearly see the emissivity is increasing while we reduce the size, which is a different picture of the Planck's law. I also look at energy dispersions of the nanoribbon, and the dispersion shows the two main types of the dispersions. First of all, the one curve is like a line, and the second one is confined mud like surface phonon Pleiades. Indeed, this energy regime is within the radial band, which is supporting the surface phonon Pleiades. The high K value in the dispersions can be analyzed by converting it into the effective wavelength by using these relations. K equals to the 2 pi over the wavelength, the lambda. Again, this energy regime is around 10 micrometers, but these radiative energies can be confined at the surface by shrinking the size of the wavelengths even below the 1 micrometer. So you can indeed imagine it's like a thermal antenna. from the dispersive radiation in the free space with 10 micrometer wavelengths, you can collect the energy at the small surface. Even we reduce the size of the structures, and we can still receive or emit the large amount of the energy. How about we further reduce the size? The emissivity will keep increasing until the size becomes below half of the wavelength. Too small size of the emitter cannot be considered as a surface, so it will eventually decrease emission as much as they lose the absorption capability. While we reduce the width from red to green and sky blue curves, and you can see the emissivity keep increasing. And when it belows the 500 nanometer width, it will start to decrease. It shows how the enhanced emission by surface photopollutants is related to the size. And I further engineered the emission by surface photopollutants using heterostructures. For instance, in our experiment, I used the gold metal island on top of the suspended silicon dioxide ribbons. Metals and polar dielectrics have different dispersions of permittivity. Gold follows the drilled model, and silicon dioxide follows lowland model. Gold has a peak of energy dispersion near the plasmonic frequency in UV, and silicon dioxide has the peak in the low energy regions in infrared range. Also, gold has a more broader dispersions than the silicon dioxide, and those are the main difference characters between the plasmon and photopollutants. Polar dielectrics are the good candidates to have a strong response in the infrared rhythms, but it has a too narrow effective energy range when it has alone itself. So that is the one of the reasons why we could only observe 0.1 and 0.2 emissivity in the earlier study. So now we make the heterostructures, including both gold and silicon dioxide. But with the plasmonic broader dispersions, we can modify the dispersion of the surface photopollutants in the infrared region as well. Again, 10 micrometer infrared wavelength corresponds to the room temperature thermal energy, so I'm more focused on the change in the infrared regions rather than the UV. The heterostructures could make more broadened response of the surface photopollutants, and we would like to confirm with the experimental measurement. Our previous measurements were done by measuring the multiple samples with various lengths. However, the approach is not suitable for complicated structures with unknown thermal properties. First of all, we don't have bulk thermal conductivity information, and we cannot make sure that all fabricated samples have the exactly same surface structures, especially with the random metal dots. So we developed the measurement platforms in frequency domain. Rather than changing the physical size of the samples, we control the heating frequency, and the thermal penetration depth will be determined by the heating frequency. At very small frequency, the penetration depth can be much larger than the sample length, so the effective heated surface to contribute to the radiative heat loss will cover the entire sample length. It represents maximal radiative heat loss. And if the penetration depth is not long enough, the effective surface area will be small. Therefore, we can use only one sample with controlled heating frequency instead of making multiple different lengths of the samples. I use the same thing model, but solve the equation in the frequency domain. Similarly, we have an M parameter. So if the M equals 0, there will be no radiative heat loss. And we can find a suitable M parameter to fit our experimentally measured data shown with the diamond symbols here in this graph. And here the temperature difference from these two curves are due to radiation. Models and experimental data were very well matched. And eventually, we can extract the emissivity by analyzing the analytical modeling. And here I summarize the emissivity of gold and silicon dioxide. And we achieved a highly enhanced emissivity of 0.46, and compared to the silicon dioxide level with a 0.1 emissivity, it's a highly enhanced. And also the stronger emissivity can be visually observed using the IR thermal camera. We made the UCSD patterns on top of the silicon wafer. And when the pattern includes both gold and silicon dioxide, the infrared radiation becomes stronger. So we can clearly see the UCSD pattern work through the IR thermal camera. All right, and then let me summarize my talk. The presented study suggests a way of thermal engineering using photonic structures so that we can achieve the coherent feature of thermal energy similar to that that we commonly observe from light. Implant thermometry was developed to quantify the emissivity of a single nanostructure, and the enhanced thermal emission has been observed by utilizing the coupled energy of photons and optical photons by surface photon pollutants. I'd like to thank my collaborator from UC San Diego and Lawrence Berkeley National Lab, and this study was supported by the NSF and DOE. Thank you.